I hope you're all doing good today. I am Mr. Ish. Thank you for joining me for this video. When you are in your chemistry exam or test and you have a comprehensive titration question to worry about, the first thing you want to do is not to panic. I'm going to show you a comprehensive question here, but we're going to make it very easy for all of you. The technique that you see here is a technique you want to follow, and I guarantee you your answers will come out right. What is our scenario here? We have 100 milliliters of acetic acid, which you know is a weak acid. It's 0.2 molars. So we have 100 ml of a weak acid, 0.2 molar, and it's titrated with a strong base, 1 molar NaOH, sodium hydroxide. We have to find the pH of your entire system at 2 milliliters of that strong base, 20 milliliters and 22 milliliters. The Ka for that weak acid is 1.8 times 10 to the minus 5. So we're looking here at that 2 ml first, right over here, and then we'll go. Now when you're looking at that, you know, the very first thing you want to do is compare your moles acid to your moles base, because that will tell you how everything will play out. Everything has to be converted into moles. You know, molarity is equal to moles over volume. Moles is equal to mV. Convert everything into liters. I have 100 milliliters, which is 0.1 liter times 0.2 molar of weak acid. That'll be 0.02. Look right here, I have 2 milliliters. You have to convert that into liters. You'll do 2 divided by 1000, and we have 1 molar of that, so it's 0.002. And you know now which one is smaller. This is larger, that's smaller. Here your acid is larger in terms of moles with regards to the base, so this will dominate the system. Your equation will be this. Because you do have base over here, you will have to write this. HA will be your weak acid plus your base OH minus. You will have here a conjugate base which will develop, and water. Water is irrelevant, so you keep that out. But look, you can do start, change, and end. What are you starting with here are these items you just determined. Moles, 0.02 moles, 0.002 moles, 0 moles. Now what do you do from here? Well, you don't have to do any x's over here, because we know however much base we have, which is less in terms of moles of acid, it will neutralize your acid to the greatest extent possible by fully consuming itself. It's going to consume itself, and in the process it's going to affect everything else. You're going to have this 0.02. Remember, we're not doing x's in here because we already know what we have here in the system. We're not looking here at anything with regards to initial conditions. We have something already at play, and that something, which is your base, will affect everything with regards to their amounts. 0.02 minus 0.002, we have 0.018. When you have a system where your weak acid is still more in terms of your base, but you have your known quantities, this is the equation you want to use. pH is equal to pKa plus log conjugate base divided by conjugate acid. Why are we using this? Because now the system is affected by the interplay of both of these items, where still this item is dominating. Simple as that. And this right here can be your pKa. How do we determine pKa? Well, pKa is equal to the negative log of your Ka. I'm going to do 1.8 exponent 5 minus, I'm going to do a log of it and minus, it's a 4.744. That's what I have. 4.744 plus a log of your items in terms of their quotient, 0.002 divided by that, 0.002 divided by 0.018. It's nothing other than now a simple calculation, and I'll show you. 0.002 conjugate base in terms of moles divided by 0.018, your weak acid in terms of moles. You don't have to convert these into molarities. They're like term units, so you keep them as is. This is your quotient. Do the log of it. It's a minus. Add it to your pKa, 4.744, and this right here is your pH of this system. When 2 milliliters of strong base have been added, 3.789, which I will round up to 3.79. That's your pH. So this question is done. Remember, we have an interplay of both known quantities, so look at this equation where you are still not at the equivalence point, because your weak acid is still dominating in terms of your moles when compared to the moles of that strong base. Scenario number 2, 20 ml. Well, convert everything into moles. I have 100 ml, which is 0.1 times that. I have 0.02. 20 ml, which is 0.02 liters, times that. I have a 0.02. We have a situation here of equivalence point. The species in terms of their moles are equal to each other. How do we proceed? Well, you proceed with your basic equation. HA plus your base, strong base, will give you your conjugate base and water. you can do your start, change, and end. You're obviously looking at your starting quantities 0.02, 0.02, and 0. You're gonna actually neutralize this to the fullest extent. This base will neutralize the acid to its fullest extent, which is here 0.02, and it will add in terms of this concentration by 0.02. What do you have? 0, 0, 0.02. Everything has been neutralized, but I have this amount in terms of conjugate base in moles. Now what I need to do is determine the pH of the system, but I have to realize before I do that this will now undergo a reverse reaction because there's nothing else present. It will undergo a reverse reaction to regenerate what you were starting with, HA and OH minus. But what will you feed here in terms of these items? It will not be your moles. Convert this into molarity. Molarity is equal to moles over volume. What's your volume over here? Well, it's equal to the total volume. You had 100 and you've had 20, so that's 120 ml or 0.12 liters. Moles divided by volume is your molarity. 0.02 divided by 0.12, that's the molarity, 0.1666, which you'll feed in right here. That's what is going to be your initial conditions now. You have 0 here, but now this is the initial conditions of this setup. You're going to do minus x plus x plus x. This will be here in x. Here you'll have a 0.166 repeating minus x. Since you have a conjugate base now driving the reaction, earlier it was the acid where a Ka would be in effect, but the conjugate base will now make sure that the Kb comes into effect. Kw is equal to Ka times Kb. Kb is equal to Kw divided by Ka. 1 times 10 to the minus 14 divided by this. What do you get? 1 exponent 14 negative divided by your Ka, 1.8 exponent 5 negative. You're getting 5.5 repeating exponent 10 minus. So we'll keep that. What's our Kb expression? It's this times this divided by that. X times x divided by 0.1666 repeating minus x. All of this is equal to your Kb, which is 5.55 repeating times 10 to the minus 10. Because this value here is so small, like very close to 0, you can literally cancel out that x and eliminate the need for getting into quadratic equations. X squared is equal to this times that. 5.55 repeating times 10 to the minus 10 times 0.166 repeating. X here, the concentration will be equal to your hydroxide ion concentration, which will be equal to this product and its square root because it's square. I have 5.555 exponent 10 minus, I'm going to multiply that by 0.16666 as you know, and I'm going to do the square root of this, which is 9.622 times 10 to the minus 6. That's your hydroxide ion concentration. 9.622 times 10 to the minus 6. I know my hydroxide ion concentration is this. So what do I do now with this? I do the POH. POH is equal to negative log OH minus. I have this value still on my calculator, 9.622 exponent 6 minus. I'm going to do the log and minus, it's 5.016. POH is equal to 5.016. I know that 14 is equal to pH plus POH. So pH must be equal to 14 minus this value, 5.016. And it's easy. I have the value here on my calculator. I'll negate it and I'll add it to 14. My answer is 8.98. That's the pH of this system. When 20 milliliters of strong base have been added, 8.98. And your answer should be good. So you've seen how everything came into play. At equivalence point, moles of this acid, weak acid, and moles of strong base are equal. It'll consume both of these. You're going to end up going at the reverse reaction. You'll switch from a Ka to a Kb. Your calculations will be then determined by that Kb expression. You're calculating for hydroxide, which will give you your POH, from which you'll determine your pH. So this question has been completed. Now we are here at this very last one, and it's easy because now you know literally you're past equivalence point, the strong base will dominate. But again, look at everything like this. HA plus your strong base, weak acid, strong base. You'll get your water, but you'll also get your conjugate base. We have a start, change, and a end or a final. What's going to be the values which you'll feed in? Well, you have to determine. We have 100 milliliters, which is 0.1 times 0.2, that's 0.02. I have 1 molar of that, that's going to be 0.022. This right here is dominating, its larger mole quantity, 0.02, 0.022. Obviously this is the smaller amount, it will minus because it's going to affect everything else. It's going to get consumed because it's fully neutralized by the excess strong base. Obviously, that's going to add over here because it will determine how much conjugate base you have. You have to do this calculation here. 0.022 minus 0.02. You have 0.002. Now look at this. You have a certain mole quantity of a strong base, a certain mole quantity of a conjugate base. Which one is relevant, which one is not? This right here is irrelevant. This is relevant because this is a strong base and it will drive and determine your pH. This right here is in moles. Everything right here we're looking at in moles converted into molarity by looking at the total volume. What's your total volume? 100 plus 22. So it's 0.122 or 122 milliliters, 0.122 liters. Molarity is equal to moles divided by volume. Divide these two items, you'll get your molarity. 0.002 divided by 0.122. This is what I have, 0.01639 molar. Molar of what? Hydroxide ion. My hydroxide ion concentration by means of the mole calculation is 0.01639. I can do the pOH, which is a negative log of this, and let's do it. Log and minus, I'm getting a 1.785, and then obviously I can do pH is equal to 14 minus pOH, and I can negate this value from 14 and we'll get our pH 12.2. This system with the following weak acid parameters and having 1 molar of 22 ml strong base added will now have a 12.2 pH, and your answer should be good. So you can see at 2 milliliters of strong base we have 3.79 pH, at 20 ml 8.98, at the equivalence point. Past the equivalent point we're jumping up to 12.2, which is basic. This right here is acidic, this here is a slightly basic, and this here is a very basic solution, but this here is your equivalence point. I've shown you everything. This is the technique you want to follow. Just don't panic and look at everything logically. Have a good day.